Hello, everyone, and welcome back. In the previous few videos, we've focused a lot on understanding real numbers. And this includes understanding their subsets as well, such as the natural numbers, the integers, and even the rational numbers. Now, we've sort of poked and prodded the real numbers from a number of different angles. We focused a lot on sequences early on. We talked about what it means to be a dense set, an open set, and we even talked about counting or countability of subsets of real numbers. Now, what we're going to start talking about in this lecture and a few of the ones going forward is functions. And now we have a strong intuition of how we can understand the real numbers. This acts as the domain and range of the functions that we are going to be talking about. And therefore, we should have a strong intuition about how we can approach these functions using a lot of the techniques that we've already developed and a lot of the, say, intuition that we've built up. Now, in particular, what we're going to talk about today is a concept you may be familiar with, and that is limits of functions. So we're going to talk about what it means for a function to approach a value as the domain is approaching a value, or as some element of the domain is approaching the value. Now, all of this is going to be made precise. Of course, now we're sort of introducing a new aspect of this course. It's going to require a few definitions. So let's go ahead and jump right in. And the first definition that we need to talk about is that of what's called a cluster point. So, like we do with most classes, we start with a definition here. So we say a point A is called let's put it in red to highlight it, a cluster point. So we'll talk about what this means in a moment. Let me just write it down. Of the set D. So D in this case is going to stand for domain, but we'll get there in a moment. If and only if. For all, in this case, delta greater than 0, there exists an X in the domain such that 0 is less than the distance from A to X, which is less than delta. Okay, so what does this actually mean, right? So the first thing is the absolute value of X minus A less than delta. This looks a lot like what we've done with convergence of sequences, right? That means that we are getting close. But the important aspect of this is, in fact, the left-hand inequality. And this tells you that the distance from X to A is in fact non-zero. So X does not equal to A. So what's a cluster point? A cluster point is a point in the set D that you can get close to without actually getting to it. All right, so that's how you should think about that. So this means close to, and this is not actually at. Right, so this is sort of informal, right? Maybe this isn't the best way to write this, but that's how you should be thinking about this. And so let me give you some examples. The interesting thing here is that your cluster point doesn't have to be in the domain. So let's say let D equal to the set 0 to 1, where 1 is not included. So i.e. 0 is less than or equal to X, less than or equal to 1. Okay, sorry, less than 1. So then the set of cluster points of D is the closed interval 0 to 1. Now, I'm going to leave this for you to sort of chew on and think about for a moment, but it's pretty easy to see that anything inside that interval is itself a cluster point. And that means, you know, if it's in the interval, you can sort of wiggle left or right, and you can always find points that are as close as you want to it. The interesting aspect of this is that you've sort of closed off the domain and included 1. And this might be easy to see, right? Because again, the definition of a cluster point says I don't actually have to be at it. I have to be able to get close to it. But of course, since X is less than 1 here, you can get as close to 1 as you want without actually being added. So that's the sort of intuition here. Okay, let's look at another interesting example, and this is coming from a sequence. So let D equal to the set of 1 over n, where n is a natural number, right? So 1, 1/2, a quarter, a third, right? All of this. I think I jumped in the middle there, but that's okay. There's only one cluster point. D has only one cluster point. Maybe pause for a second and think about what it is, but it's going to be 0. And why is that? Well, 0 is the only number in the, that you can get close to without actually getting at, right? So for example, 1/2 is in D. You can't get close to 1/2. The closest you can get is to 1/3. That's the closest element in D to 1/2. So if I pick something, if I pick delta smaller than the distance between 1/2 and a third, well, then that means that this is not a cluster point, because the only way I can get close to 1/2 is being at a half. But we know that 1 over n converges to 0. We can get as close as we want to 0 without actually getting at it. And that tells us that we have a cluster point at 0. And the interesting point here again is that your cluster point isn't in your domain, right? That is the sort of exciting aspect of this. Okay, so with this idea of cluster points, this allows us to understand a limit, because if you think about limits, if you learn them in maybe your introductory calculus classes, then limits are talking about approaching. It's getting close to, but not at. That's the important piece here, and that's where cluster points are useful. So let A be a cluster point of the domain. Now we're going to call this D sub f. This means of a function f. Okay, so a domain of a function f. So that means all of the values that you get to pick to put into the function, that's what we call the domain. Then we write the limit as x approaches a. So this is important. It tells us limits are only defined in terms of cluster points, is equal to L if and only if we have, for all epsilon greater than 0, so again, we're using limits just like sequences, but in this case, you have to have epsilon and delta such that if x is in your domain and it's close to but not at a, this tells you f of x minus f of a, or sorry, minus L, pardon me, is less than epsilon. Again, what does this mean? Limits mean approaching. So that's approaching right there, right? It means I'm not actually at it, I am close to it. That's why you need a cluster point. And this says that if you're close enough to the cluster point, then you are close to the limit. That's what this is telling you here. So let's take a look at some nice examples. So the first example, we're going to deal with a linear function. So let m and b be in R, and we're going to assume m is not equal to 0, because if m is equal to 0, we're going to deal with a constant function. You've probably seen m and b before. This is going to be a linear function. So let's let f of x equal to mx plus b. So it's a line, right? Then we claim that the limit as x approaches any a in the domain of mx plus b is equal to ma plus b. All right, so again, if you took a calculus class, this is not exciting to you, but the exciting part is actually doing this properly, right? Maybe you just learned in calculus that this thing is continuous and then you can just sort of plug in values and limit, but why should you be believing that, right? You have to be able to prove things. In mathematics, we're all skeptics. We don't believe anything until we can prove it ourselves. And that's the approach that you should be having as you're going through this class as well. So in this case, we're going to say let epsilon be greater than 0. We're dealing with a limit. We always need it. And we need to find a delta greater than 0 such that if x is close to delta, or sorry, if x is close to a, this implies that m times x minus a, sorry, yes, x minus a, sorry. Sorry. Let's do this properly. Sorry, I skipped a step on you. Mx plus b minus ma plus b is less than epsilon. Pardon me. But this thing is the same as m times x minus a, right? The b's are going to cancel each other out. And so what we want is to have, again, we want to find delta so that x minus a is small, and that will guarantee that m times x minus a is less than epsilon. So we can take delta equal to epsilon over the absolute value of m. Again, I assumed m is not equal to 0 to find that when 0 is less than x minus a, which is less than delta, which is equal to epsilon over the absolute value of m, we have, this was m times x minus a. Well, this is equal to the absolute value of m times x minus a, which is less than or equal to, since this is delta here, which is equal to the absolute value of m times epsilon over the absolute value of m, which is equal to epsilon as desired. So you can see how the game works here, right? The game is that I give you epsilon, you need to find delta. And that's what we did, right? That was the main piece up here. I found delta. And in this case, delta, just like finding capital N with sequences, it depends on epsilon. As long as epsilon is arbitrary and you can still make it work, that's fine, right? That's how you play this game. So it's just like sequences. Sequences say find capital N, limits say find delta. Okay, let's do another one, and it's going to look like it's going to be a lot of work, but I'm going to show you that it isn't. So we claim that the limit as x approaches 1 of x squared minus 1 over x minus 1 is equal to 2. Okay, so you probably did this in your maybe introductory calculus class if you took one, and you know that you can factor the top and you knock things off and you just sort of plug x equal to 1 in here, right? How do you do this with analysis? Exactly the same, actually. This is the cool thing, right? So you might maybe looked at this and you were starting to get a little seasick and thinking, oh, this is going to be a lot of work, right? But turns out that it won't be, actually. So since the concept of a limit does not permit x equal to 1, we can say for all x not equal to 1, our function x squared minus 1 over x minus 1, this thing is just a fraction, and we can knock off the common factor just like you did if you do this in calculus. And clearly, this is approaching 2 as x approaches 1, right? And the reason for this is from previous example. Right, that's now a linear function. M is equal to 1, B is equal to 1. Now you can just evoke what we did for lines. And so that's why I just wrote this, this right arrow. I didn't do any analysis because it just falls into the previous case. Okay, so 3. Let's consider a piecewise function now. F of x is equal to, say, 0 if x does not equal to 0. And 1 if x is equal to 0. So this is a discontinuous function as we typically interpret it. But then let's look at the limit as x goes to 0. Well, this is f of x. But as long as, remember, the limit does not permit you to actually look at the value 0. So that means, as long as x does not equal to 0, you're always just looking at a function that is 0, right? Because that comes from this first piece right here. You're not allowed to look here. And so clearly this is just a limit of a constant. And so it's just going to be 0. And it is worth noting here for what we'll talk about later. And if you're familiar with this thing is discontinuous because this does not equal to the value at 0. All right, let's do one more. Let's again consider a piecewise function. So in this case, f of x is equal to 1 if x is greater than or equal to 0, and 0 if x is less than 0. Sometimes this is called the Heaviside function. This is named after a mathematician and physicist named Heaviside. So it's 1 on the positive values, 0 on the negative values, and you sort of have this step up that's discontinuous, this jump at 0. Well, then the limit as x goes to 0 of f of x does not exist. So that means that we cannot take delta. So this means, in fact, we cannot take delta greater than 0 small enough to small enough so that 0 is less than x minus x minus 0, pardon me, since where a is equal to 0 in this case, less than delta, to get f of x minus L is less than epsilon for some L. Now, why is that the case? Well, because, so let me go to the next page. So for x less than 0, f of x is equal to 0, which implies that 0 minus L is less than epsilon, which implies that the absolute value of L would be less than epsilon. But also, for x greater than or equal to 0, f of x is equal to 1, which implies that 1 minus L is less than epsilon. And so taking epsilon, say, equal to 1/2 means we cannot find such an L, right? Because this would mean that you need to have L within a distance of 1/2, smaller than a distance of 1/2 to 0, and smaller than a distance of 1/2 to 1. That's not possible. You can never do that. So you're never going to be able to find a delta small enough, because that delta is allowing you to take positive and negative x's in here to find that f of x minus some potential limit is less than epsilon. Okay, so let me give you a nice theorem, because this theorem will probably, there are lots of important theorems that you're going to learn in this class, but my guess is, the one you're going to get the most mileage out of is this theorem right here. Because what this theorem does is it lifts that epsilon delta definition of a limit that I just presented to you and poses it in terms of sequences. And again, we've done 9 lectures prior to this one. A lot of them dealt with sequences. You're probably pretty good at sequences now. And so that means that you can sort of lighten the load on your mind here a little bit, because you can think about limits now as in terms of sequences, as opposed to this epsilon delta definition. So let's say, suppose A is a cluster point of the domain df of a function f. Okay, then the following two statements are logically equivalent. And I'll speak about this in a moment. So the first one, the limit as x goes to a of f of x is equal to L. And the second one is that for every sequence of points, xn, which belongs to the domain of f, but not the cluster point A, such that xn is approaching A, we have the sequence. So you get a new sequence by plugging in each element of your sequence into the function. So that's a sequence in the range now of your function f. This is approaching L. And we call this, maybe I'll put this in green, this is called the sequential criterion for limits. Now, if you take a look at the statement of this, it says the following are logically equivalent. Now, what that means is that saying one of these things is equivalent to saying the other. They mean exactly the same thing. They are logical synonyms, if you'd like to think of it that way. So that means that if we're going to prove this thing, we need to prove that if we say one thing, we can get the other thing. Okay, so that means there's two things that we need to prove. So I'm going to write it like this. So this is, or sorry, we're going to say 1 implies 2. So 1 implies 2. So if I say the limit of f of x is equal to L, that is the same as the sequential definition. So suppose that the limit as x approaches to a of f of x is equal to L. Now remember, that is just shorthand for, you know, that huge definition that we started with today. And consider any sequence xn which belongs to the domain but is not equal to a, such that xn approaches a as n goes to infinity. So then we know for all epsilon greater than 0, there exists, so this is using the proper definition of a limit in terms of point number 1 here. So I'm going to turn this back into the definition. So for every epsilon bigger than 0, there exists a delta such that if x is in the domain of f and 0 is less than x minus a, which is less than delta, this implies f of x minus L is less than epsilon. So again, this is just a definition, but this is how you should be doing proofs. You write down what you're assuming, what you want to, what you need to have, and then what you know from your assumptions. This is a very, very good way to approach proofs because it helps you have everything on the page that you're going to need. Okay, let me go to the next page. I'm running in a room here. So, but xn is approaching a. This tells us, this implies that there exists some natural number such that n greater than or equal to n implies that 0 is less than xn minus a, which is less than delta. The fact that you have the lower inequality comes from the fact that xn is taken from the domain minus the value of a. And you can always say, you know, whatever the value of delta was that for the given epsilon, you can squeeze yourself in here, get yourself delta close to the limit. But then this implies that since your xn's are close enough to a, your f of xn is close enough to the limit. And so since epsilon is arbitrary, you get that f of xn is approaching L. Okay, so the next thing we want to do is we want to prove that the other way around works. So if I give you the sequential definition, I'm going to show you that the epsilon delta definition works. So we need to show that the limit as x approaches a of f of x is equal to L, right? So here's what we'll do. We'll show that this is actually, we're going to assume that this is false, and then we'll find a contradiction. So assume that this is false to find a contradiction. Okay, so that's the goal here. We're gonna assume it's false, and we'll find a contradiction. So, but if one were false, so we're gonna have to sort of invert this, then there exists an epsilon. So we're inverting, right? Remember, if you're going to invert these or negate statements, for all becomes there exists becomes for all. So that means that there exists an epsilon positive such that no matter how small we take delta, there exists, right? So for all becomes there exists an element of your domain that is delta close to A, and yet f of x minus a, f of minus L, pardon me, is greater than or equal to epsilon, right? So I logically inverted that. So how am I going to do this? In particular, we're going to take a sequence of deltas. So delta is equal to delta sub n is equal to 1 over n. Now this says that epsilon is fixed for every delta bigger than 0. So each one of these is bigger than 0. That's fine. I can always find an x. So then we get an xn such that, well, such that 0 is less than xn minus a, which is less than 1 over n, that's delta n, and f of xn minus L is greater than or equal to epsilon. But now, this tells us that the xn's are in the domain and are not equal to a, and the xn's are converging to a, but f of xn is not converging to L. But this clearly contradicts 2. This contradicts statement 2, which was assumed to be true, right? And that's our logical contradiction. So again, what did we do here? We said, well, assume that the sequential criterion for limits is true. Then we're going to show that the epsilon delta definition is true. What we did is we said, imagine the epsilon delta condition is false. So then what I can do is I can find a sequence that's converging to A, but f of xn is not converging to L. But of course, this contradicts the sequential definition, right? I found a sequence that satisfies the hypotheses of the sequential definition, but yet f of xn is not converging to L. That's the issue, right? That's where the logical inconsistency comes from. Okay. The nice thing about this is that the sequential definition allows us to carry over most of our understanding of sequences that we built up over the first few lectures in this lecture series. So in this case, we can get some really, really nice results about manipulating limits and making things easier for ourselves. So we have an immediate corollary here. Let's suppose A is a cluster point. So we always need cluster points when we talk about limits. This is something you're going to you're going to have ingrained into your mind after this, of the intersection. So we're going to talk about two functions now. Intersection. The domain of F and the domain of G. So of the domains of F and G. And suppose further that well, the limit as x approaches a of f of x is equal to L, and the limit as x approaches a of g of x is equal to L. Okay, so I have two limits now. It's equal to m. Sorry, it can be different. Pardon me. This is similar to what we did with algebraic combinations of sequences, right? This is actually going to be the algebraic combinations of sequences version for functions. Okay, let me list all of the results on the next page here because I'm out of room, but here's the idea. I assume that I have two functions that as x approaches a, their limits exist. I call those limits L and M. Then what happens? Then 1, the limit as x goes to a of, if I add or subtract these two things, this becomes the limits added or subtracted as well. The second one is if I multiply these two things. So this gives me, let's say, f times g of x. This gives me L times m. Similarly, for 3, if I want to divide these two things, right? So the classic in terms of these limits, well, then this becomes L over M, provided M does not equal to 0, and that A is a cluster point of the domain of F over G, right? So there's a little extra stipulation here, but it's not that big of a deal, right? It's something that you're probably not going to think about too much, and you know the cases where it fails, right? You can't divide by 0. That's pretty much all that's happening. Now, why is this a corollary of the previous result? Well, you can just pose everything in terms of sequences, right? Remember, we proved all of these results for sequences already. Well, now we know that we can pose limits in terms of sequences, and life is good. So let's just prove number 1. So let's consider a sequence of points, and these are going to be xn that belongs to the intersection of these two domains and does not include the cluster point A, such that xn is approaching A. Then, well, this is pretty simple because we know that f plus or minus g of xn is equal to a sequence f of xn and g of xn added or subtracted. But since these are convergent sequences, now we know that they themselves are sequences, and so they can be added or subtracted in the limit. Sorry, I keep forgetting the minus here as well. This, from our results on algebraic combinations of sequences, right? So again, we know that convergent sequences, if you add them together, you get the limits added together, and so on and so forth. And so this is really just a consequence of the fact that we can now pose these things in terms of sequences. So the proofs of part 2 and part 3 are the same, are similar. So I'm going to leave those out because it's, it's just, again, evoking those algebraic combinations of sequences. So it might be important for you to go back and take a look at what we did with those algebraic combinations of sequences. If you're really bored, try and prove them, right? Try and prove number 2, try and prove number 3, and it should be similarly short because you're essentially just evoking those algebraic combinations of sequences. Okay, now I want to close with one more definition. So again, we have talked about using cluster points. So that is, limits approaching some finite point. Now, of course, if you went through a calculus class before this, you know that there are other limits that we're interested in, and those other limits are as you go to plus or minus infinity. So let's take a look at what happens in this case. So let's just get ourselves a nice formal definition here. So we define limits at infinity and also, so let's put this in red, one-sided limits as follows. So 1, if the domain df is not bounded above, right? So you can go all as far as you want to the right. You can go, all the way to quote unquote infinity, right? Infinity is not actually a number. You should really sort of think of it as a direction, but nonetheless, you can go all the way up. So it's not bounded above, right? Its supremum is equal to infinity. We say f of x approaches some limit L as x goes to infinity, provided that for all sequences, right? So this is the real importance of the sequential criterion now, is because we can use everything that we know about sequences, all the work that we've done, we can carry it over to limits. Carry it over to limits and carry it over to functions. So for all sequences, xn in the domain of f, such that xn goes to infinity. Remember, we have a precise definition of this thing. That means that, for all m greater than 0, you can look far enough in the sequence and every element of the sequence beyond some point is bigger than m. This means we have f of xn is approaching L. So that's a limit at infinity. You can do the same thing for minus infinity. I'm not going to bother with it because you are smart. You're watching this. You understand that. You can just flip around and you can put the minuses in here. You just need to know that you're not bounded below in this case, right? You can go all the way to the left. Similarly, let's do the one-sided limit case. So part 2 of this definition, if A is a cluster point of the domain of f intersected with a to infinity, so just the sort of right half of the real line from a and up, we say that the limit as x goes to a from the right. Again, if you took a calculus class before this, you probably are familiar with this notation. The plus means the right, right? We think of going to the right as the positive direction. Provided that for all sequences, xn in the domain of f intersected with a to infinity, such that xn is approaching a. So you're approaching a from the right-hand side now. We have f of xn is approaching L. And in this case, we write f of a from the right, right, is equal to, so this is just a shorthand notation, a to the right of f of x. And again, you can do the same thing from the left. I'm just not going to bother with it because it's just, it's just a lot more writing for something that is not really that informative, but you would say the domain from minus infinity up to a, so the left part of the domain that includes a, or that is below a, and then we have, then in that case you would write the limit as x goes to a from the left. You have a negative sign up there, and you can write this thing as a to the left, right? So it's just a vague notation here. Actually, it's not vague. It's actually quite descriptive. But again, I'm not going to bother with that. And the other thing that I just want to point out here is, in all of my definitions here, I have sort of purposely not told you that L is a real number, right? And this will still work if L is equal to infinity, because again, we have proper definitions of what happens as a sequence. If we say, sequence right arrow infinity, that means it diverges to infinity. But again, we have a perfectly logical definition for this thing. So because this entire definition is posed in terms of sequences, it is perfectly fine for L to be plus or minus infinity as well. It doesn't have to actually be a limit that exists. You can carry this over, right? You can say f of x approaches infinity as x approaches infinity. F of x approaches minus infinity as x approaches infinity. Same thing can happen here for the second condition. And this comes up a lot, right? This would come up when you have asymptotes of a function. Think about 1 over x. If you're approaching 0 from the right, that thing is going to positive infinity. Same thing, if you're approaching 0 from the left, it's going to negative infinity. So you have this divergence that you're probably quite familiar with because you've probably worked with this function quite a bit. But nonetheless, this is just formalizing a lot of what we already know. And what we've really done today is given you the exact descriptions of what you have probably already seen in a previous calculus course, if you took one before this. So what we're doing is we're making everything precise. And as I said, be a skeptic. That is your duty following these lectures. And if you're doing work as you're going through, everything is something you should be skeptical about in this class. And you can only believe it if you can prove it yourself. And so you have to follow along with the proofs that I've done, make sure that you understand them, make sure you can recreate them step by step, and then see if you can do exercises on your own and make sure that you can, use these definitions to come up with things that you might have already sort of taken for granted in a previous class.